Water is something we take for granted a lot. California's been in a severe drought, and so we've been much more aware of the value and the need for water. But chemically, water is a very strange substance. We know that it's, critical for life. Water has a low molar mass, and yet it's a liquid at room temperature. And most things with similar molar masses are gases at room temperature. And the reason that water holds together as a liquid is due to its hydrogen bonding. Water is sometimes called the universal solvent because so many things are soluble in it. Most of the chemical processes that occur in your body occur in aqueous solution with water as the solvent. It has a very high specific heat capacity. Metals have specific heat capacities less than 1 joule per gram degree Celsius, and water is 4. It's very high. That high specific heat capacity helps to moderate the climate, keep the temperature fluctuations to a minimum. Water expands upon freezing. This is unusual. Most solids are more dense than their liquids, but that's not the case for water. The whole boiling point thing is illustrated here. If we compare compounds with hydrogen for the different families or groups in the periodic table. So here in the orange is group 4. Is group 4, isn't it? Yeah, group 4. And the yellow is group 5. And the blue is group 6. And then the halogens, group 7, are in here. What we see is, with group 4, is we see a fairly linear trend here in terms of boiling point versus period in the periodic table. So carbon is smaller, silicon's larger, it's right below, and then germanium, sounded like geranium, and then tin. As the molar mass, the size of the molecule increases, the strength of the dispersion forces increases, and we see that the boiling point increases. This is a trend. Well, when we look at the group 6, there's this nice trend with sulfur and selenium and tellurium, but water is bucking the trend in a big way. Right? We expect this line to be more like that. We'd expect the boiling point of water to be down here, but it's not, because water has hydrogen bonding. Hydrogen fluoride and ammonia also buck the trends from their groups because they also have hydrogen bonding. Remember, hydrogen bonding is hydrogen and fluorine, oxygen, or nitrogen. So these three have higher than expected boiling points. And that's a real good thing for life on planet Earth, because if water boiled at minus 100 degrees, things would not be as they are. Water pollution is certainly a concern. There's two different kinds of water pollution. There's biological and chemical. Biological contaminants, various microorganisms, and this commonly enters the water when animal or human waste is dumped into bodies of water or is leached into bodies of water. If you have a stream near a pasture, well, it rains and it washes things from the cow poop into the stream, and so you could get sick if you drink the water out of that stream. It's not a good idea to use the water from that stream to water the strawberries, because then people get E. coli poisoning from eating the strawberries. You can treat biological contamination sometimes just simply by boiling it to kill the organism, or you can use chemicals such as bleach to kill the organisms. Chemical contamination comes from industrial and household dumping, cars leaking fluids onto the roads, pesticide and fertilizer use. Many of these contaminants are non-volatile. They're not going to rapidly evaporate. They're not alive, so killing them is not, doesn't do any good. So boiling the water is not going to help at all. In fact, it may make it worse because when you boil water, some of it escapes as a gas and you actually concentrate the pollutants. So the different types of water pollution need to be treated differently. And we'll stop here.